The last time we said a coterminal angle were angles that have coincident terminal rays. In other words, the same terminal ray. For instance, these two angles, 60 degrees and minus 660 degrees, are actually coterminal angles. Right? How do you tell they're coterminal, right? The idea is that they have coincident terminal rays. Here's 60 degrees. I'll divide the first quadrant into three equal parts and say, well, 30 degrees, 60 degrees, 90 degrees. Here's 60 degrees here, 2/3 of a right angle, right? And so that's one terminal ray. And then if I take minus 660, I can use my drawing technique and say, well, there's minus 360. I have to go clockwise for a negative angle. There's minus 360, and then if I add to that minus 180, that makes minus 540. And then I add to that a right angle, minus 90 degrees. Well, that's minus 630. That makes another minus 30. So if you break this one up, minus 660 into a whole rotation, a straight angle, a right angle, and a third of a right angle, I could see that as minus 360, the whole rotation, minus 180. If you just do what we did before, you can sketch it this way. Might be easier to do minus 720 back up 60. You can see. But if you break it up, you can see that it winds up in the same spot, right? So those are coterminal angles. They have the same terminal ray visually. How do you calculate that? We said you can identify them because they differ by a whole number of rotations, whether they go clockwise or counterclockwise. 360, a multiple of 360 degrees or of 2 pi. So suppose I take these two angles. These aren't obviously coterminal from just writing them down. How do I tell? Let's take the bigger one minus the smaller one. And negatives are always smaller. If I take 40 degrees and minus 320 degrees, if I wanted to see if they're coterminal, I take the 40 degrees and subtract the negative 320 degrees. And so I'd actually add them and get 360. Oh, yes, they're coterminal because their difference, larger minus the smaller, negative numbers are smaller than positive numbers. Is a multiple of 360. In fact, it's 360 itself. Every angle is coterminal with itself for this reason, right? But here's these two, 890 and minus 190. So I take 890 minus the other angle, gives 1080. Sure enough, that's 3 times 360. So yes, they're coterminal, right? If I drew a picture like that, I'd see it, but I don't have to draw the picture. I can just subtract them and see if it's a multiple of 360. Similarly, in radians, if I take 7 pi over 16, that's a pi. 16 pi over 16, these are not coterminal. If I take the larger 16 pi over 3 and subtract the smaller 7 pi over 3, I get 9 pi over 3. Oh, that's 3 pi. That must be coincident terminal rays, right? No, it's an odd multiple of pi. And what you want for coterminal, maybe you can't see back there, sorry. But the difference in these two angles is 3 pi. But we need a multiple of 2 pi, right? So the coterminal angles are those that differ by an even multiple of pi, 0, 2 pi, 4 pi, 6 pi. So it's a multiple of 2 pi. 3 pi is not a multiple of 2 pi. So these are actually opposite each other, right? 2 pi apart, they'd be a rotation apart. 1 pi more, they're directly opposite. So these are opposite angles, not coterminal angles. So it's not those, these are not coterminal. Any questions on that one? Is there enough review of that one? And then we said also, one of the purposes of these is to get an angle that points with its terminal ray in the same direction, but is a smaller number, right? So some of the problems are find a coterminal angle to a given angle that is non-negative and as small as possible. Suppose I gave you one of these for the test. This is what's done in practice. You get an angle that's negative or that's big, and you want to say, well, what direction is that? If I say that the wind is blowing at 980 degrees, what direction that is, but if I find a coterminal angle that's as small as possible, then I can figure out what it is. And the idea is as small as possible means you're always going to find an angle between 0 and 360 degrees, less than 360. That'll be the smallest possible, always between those. So what you do is you just keep subtracting multiples of 360, we're saying, until you get an angle between 0 and 360. So I can subtract 360 from there and say, well, that's going to be 620 degrees. That's still bigger than 360. That's too big. So I'll subtract twice 360, 720. That might work. Let's see, if I subtract that, I'm left with 260. That's between 0 and 360. That's the smallest possible angle I can get. So I subtract whole multiples of pi to get a coterminal angle. And then when it's between 0 and 360, that's the smallest I can make it and keep it positive. So there's that one. And then similarly, we can do this with radians. For instance, suppose I say 15 pi over 7. What is the smallest positive angle that's coterminal with that? That's a little trickier, right? But the idea is I subtract off whole rotations, I subtract multiples of 2 pi. So what can I do? I can say, well, this is bigger than 2 pi, so it's not the smallest angle itself, right? 2 pi would be 14 pi over 7. So what I'll do is I'll subtract off 2 pi, 14 pi over 7. If that's still bigger than 2 pi, then I'll subtract off 2 pi again. So this is 2 pi, a whole rotation. Now 15 pi over 7 minus 14 pi over 7. Since they have the same denominator, I subtract the numerators over that denominator. And 15 of these minus 1 of these is 14 of these is 1 of these. And here's technically how you do it if you put in every step. Don't put every step on the test, but you factor out the pi and say it's 15 minus 14 pi all over 7. Oh, that's just 1 pi over 7. I would leave this step out. 15 of these minus 14 of these is 1 of these. And so it's pi over 7. This one is less than or equal to 0 to 2 pi. So for radians, it's 0 less than or equal to angle less than 2 pi. And so this is the smallest non-negative angle that's coterminal with 15 pi over 7. I just subtract multiple of 2 pi until I get something between 0 and pi. Do that for homework, all right? And the idea is, I don't know which direction 980 degrees goes, but I know which direction 260 degrees goes, right? That's, for instance, if you're doing bearing, go clockwise from north. So if I say it's bearing 260 degrees, I say, oh, that's almost 270 degrees. It's 90, 80, 270, it's 10 degrees short. So now I know what direction this is north. It's almost west, a little south of west, right? So it's helpful for that kind of thing. And then in the plane, you'd have to go counterclockwise. But so some angles in practice, actually, they measure clockwise. Some of them measure counterclockwise, and you have to know what the system is. All right, well, the next topic then is to look at angular velocity or angular speed. What's the difference between velocity and speed? Go ahead and open thinking or something. In more than in more than one dimension of that velocity is a vector. That's right. Suppose it's just in one dimension. Suppose it's moving along a line like this. Difference between my velocity and my speed. You are right.
It's gaining and then speed is constant.
Speed is actually the absolute value of velocity. So if I move forward 1 square per second, these are foot-long squares. And I'm moving at 1 foot per second velocity and speed. But if I'm moving backwards, my velocity is negative 1 foot per second. My speed is plus 1 foot per second. So speed is just the absolute value of velocity. We'll only talk about angular speed for this class, but in general, you can have angular velocity, which is negative. And we'll say this. It can be from our equation S equals R theta for arc length S. subtended by a central angle theta on a circle of radius r. Suppose instead of having just a fixed arc length and a fixed angle, suppose I'm actually moving along a circle, right? Maybe this is a CD and I put a penny in the end and let it go round and around and around. Then it has a velocity or a speed if you take absolute value of velocity. But here's what we had before. You had an angle in standard position. It doesn't have to be in standard position. Theta. And then you measure this, put a tape measure down and measure how long that was, S, and this had radius R, then you had S equals R theta. Now suppose that you have a penny on the edge and it's going at a constant turning rate. Constant turning rate. If I sweep out this distance in a time t, then I can divide this side by t and this side by t. And suppose I let this little lowercase omega, here's uppercase omega, maybe you see in the Greek house, lowercase omega. Let omega be angle that it turns through divided by the time it takes. Right? Then this side over here can also be written as r times theta over t, right? By rules for quotients, multiply this out, you take r over 1 top times top over bottom times bottom. These are equal. So you also write this in. This is then omega by our definition. This one is the distance you travel along the edge divided by time. This is actually your speed. Right? And so we use v for speed because we already need s for arc length. And so v velocity is the same thing to within absolute value. It's just the common letter they use in physics with v for speed. Let omega equal theta divided by time. Well, what should we call it? Let's call it angular speed. Or if you allow negatives, then it's angular velocity. And just like we took distance divided by time as linear speed, then doesn't mean it's moving along a line. It just means it's distance if you stretch the tape measure out along a line. So we have these definitions. Distance divided by time, just from algebra, is still speed. But angle divided by time will be angular speed, the rate at which the angle is turning constant. Right? And now we have, from that division, just S equals R theta, divide both sides by T. We get V on the left equals R times omega on the right. Just as simple a formula. Excuse me. Relating speed and angular speed that we had for arc length and angle. Okay, so call that equation 1. And these problems, these got to be really simple too. That's the second simplest formula this semester. Actually, the problems are kind of tricky because they involve lots of changes in units, which is also a good thing to learn. But you just want to practice these. These are more practice than difficulty. So problems are deceptively tricky due to the change of units. Part of the trouble is this radiance measure being unitless. All right, so here's an example out of one of the homework problems. A wheel has a tire has a nail in it, but it's not deflating. I've had that happen before. It turns around, I hear the clicking. I quick get over to the place to get it repaired, but I don't pull it out or it gets flat right away. If it's already all the way in, if it's part way in, then you can pull it out. So a tire with a 14-inch radius, the nail in it, while the car travels at 60 miles per hour. MPH is a common abbreviation for that, right? At what angular speed it's something that's familiar to you, say feet per second. FT for feet, and S for seconds. Not angular speed, radians per second. Radians per second. Does the nail turn? All right, how do I solve that problem? And it's the application that makes it tricky here in the unit. First thing to recognize, this is the car's wheel traveling along the road. I've got a nail in there. If the car, assume the car travels without slipping, as the wheel moves over to here somewhere, nail rotates around to some position, and this arc length swept out along here, along the circle, is the same as the distance along the road, right? What you can do is say the velocity of the car or speed of the car is actually the same as the speed of a point on the rim of the wheel. So this is actually 60 miles per hour is actually V, the velocity of this nail that's going around. Nail would fly off, it would go off at 60 miles per hour. So we'll call this V, and what you do in these word problems, go through and see all the numbers that you've given in there and say, what are they? This is the velocity of the nail, V. Now, what angular speed, you also want to circle the thing that you're supposed to find. Angular speed is omega, so I'm supposed to find omega given V, and all of a sudden I get 14-inch radius, that's R. And that's what I have there. I'm given V, R, omega, just what I have in my formula. So you figure that out. You write letters for all the numbers you're given there. And you write a letter for the thing you want to find, and then you have it, and you write an equation relating them. Since by our formula there was V equals R omega, we can write now 60 miles per hour, and this is why you have to write the units in. But instead of MPH, I want to write it as a quotient miles divided by hours. That's the same thing as miles per hour. Equals R, the radius is 14 inches, times omega. And omega, I want to put in radians per second. Yeah. Okay. So the tricky thing is figuring the units on this. Can I erase the problem now?
Mhm.
So what I can do now is divide by 14 inches and say 16 miles per hour, 60 miles per hour, divided by 14 inches is omega by division. And you can write that as 60 over 14, and these behave like fractions too. This is inches divided by 1 if you like. When you have a quotient, A over B over C over D. How do you evaluate what that is in algebra? Right, you can say, oh, it's the top times the reciprocal of the bottom, right? D over C. That's one way to do it. And then you realize, oh, by multiplication, now it's AD over BC. It's top times bottom over middle times middle with fractions. Same thing with these units, top times bottom over middle times middle. So this is miles per hour inches. That's a multiplication there, hours times inches. Sometimes I'll put a times inches. Sometimes I'll put a dash, but it looks like subtract, so I'll put a dot. Miles divided by hours per inch. Well, that's not radians per second. What am I going to do? There's where the units comes from. I have to convert it. So I'll say that's actually equal to 60 over 14 miles per hours inch. And I can multiply that by 5,280 feet equals 1 mile. So I'm multiplying by 1. I'm not changing the quotient. I'm just changing the units. It's like if you had 3 yards or maybe 7 yards, you write that 7 yards times 3 feet for 1 yard, multiplying by 1, and you say, oh, it's 7 times 3 or 21 feet, right? Because the yards cancel. This is doing the same kind of thing, right? So now I can cancel the miles, and now then I also know that there's 12 inches per 1 foot, right? And so now I can cancel the inches with the inches and the feet with the feet, and I got rid of the units there, and I've got just per hour. So I've got, again, multiplying these quotients, top times top times top, 60 times 5,280 times 12, all over 14 times 1 times 1 is just 14. And all I've got left now is 1 over hours. What is that? Well, I'm supposed to get seconds, so I'm going to convert it again, right? I want radians per second. 60 times 52, 5,280 times 12, all over 14 per hour times. I can multiply that by there's 1 hour for every 60 minutes. And then I'll cancel the hours. Now I've got minutes. And I multiply that by 1 minute for every 60 seconds. Or you can save yourself a little time and say 1 over 3,600. This is easier. 1 hour for every 3,600 seconds. That's a nice thing to memorize. So you can do that all in one fell swoop if you memorize that. And so what I've got now is 60 times 5,280 times 12, all divided by 14 times 60 times 60. All right. And it's canceling per second. Is that what I want? Actually is. What I want is radians per second. Radians is unitless. So I can scratch this out and just put radians at any time. You'll see on the device is something that has an angular rate of term, and they'll say per second, and just 1 over seconds. And what is that? It means radians per second, because radians is unitless. So you can put that at any time you want, only for radians. All right, so now I have what I want, radians per second, and nicely something canceled, 60 miles per hour and 60 down here. And so I can multiply those and let's see what I get. You can also take 12 divided by 60 is 1 over 5, but sometimes that doesn't help any. So 5,280 times 12 by 14 divided by 60. Make sure when you divide here, you either put the parentheses in on your calculator or divide by 14 and then divide by 60, either way. What I get is 75.42857 radians per second. So about 75 radians per second if you round it to the nearest radian. On the homework, sometimes it's not clear how many digits to carry. Put in lots of digits and it'll count it right. It just wants you to be close enough. But I don't know how many digits it wants in some of those. We're still figuring out this. So I'll put lots of them. And there's my answer. Now, if I say round this to 2 decimal places, maybe some of the problems say that. What does that mean?
75.43.
No, the idea is that the decimal digits are the numbers 0, 1 through 9. And so this is the decimal point. So it means round to 2 places right on the decimal point. So it's right here. Yeah, and so if this next digit is 5 or greater, I round up, and if it's 4 or less, I just put this part. So I'm gonna put 75.43. I'll put this squiggly equals, you don't have to use that. I'll say it's approximately 75.43 radians per second. And leave out radians if you want. Right. So there's the rate at which the wheel turns. It wasn't that hard a problem, just D equals R omega, but you have to figure out what's what in the problem, circle them, and figure out what you have and what you need, and then all these unit conversions are kind of tricky. Now, if I ask you for significant digits, how many significant digits is this? It's different than decimal, yeah. You start with the first non-zero digit, 0 through 9, the first non-zero digit, 1 through 9, and then count 1, 2, 3, 4. So it's actually 4 significant digits that are rounded to, or 2 decimal places. Just for rounding things. Occasionally the problems ask you to round to a certain number of digits. All right, one more of these, because sometimes what happens in practice is you get, you don't want to solve for omega, you want to solve for velocity, like having the wheel rate of current, how fast is the car moving? So here's a similar problem. This is also like a homework problem. Try this. Let's do Thursday, we said. Suppose a lawnmower blade turns. Here's how they often give turning rates at 2,600 RPM, meaning revolutions per minute. And cuts a 22-inch wide path. Assuming you can keep that turning rate while it's mowing, how fast is the tip of the blade moving? That's your toe up and it's going too fast, right? All right, again, it's a very simple formula. But it says how fast, that's a hint. That's telling you what is the speed. But again, go through and find the numbers. 2,600 RPM, what is that? What letter is it, or what?
Rotations per minute?
Yeah, revolutions per minute. And so what is that? Is that V? Is that R? Is that theta? Is that something else? This is actually omega. Because it's telling you the turning rate of revolutions per minute. So this is omega. And then cuts a 22-inch wide path. What's that? It's trickier here in this applied problems.
The radius? Well, your diameter.
Yeah, so that's the diameter. So this is the diameter instead of the radius. And then how fast is the tip of the blade moving? That's asking you to find the linear velocity or speed, v. Right? So now what I have is I'm given something what I'm given v, I'm given d and omega. I can write from this. I know that the radius is the diameter divided by 2 is 11 inches. And then I use my formula, since I have R and I have omega, I have to find V. I write V equals R omega. is 11 inches times omega is 2,600. And I'm gonna write RPM as revolutions per minute as a ratio in order to use it instead of writing RPM. Now, once I write all those as ratios, I can do the same thing as or change the unit. Start this up here. I'm gonna plan ahead for a minute. Move myself in a room, hopefully. So V is then equal to 11 inches times 2,600 revolutions per minute. And I need to convert this. So how fast is the tip of the blade moving? Let's say in feet per second, something like that. Per second. I don't remember what the actual units are in your homework problem, but it's like this. What is the feet per second? I don't have feet per second. I have inches revolutions per minute. So how do I convert that? So well, I need per second. So I'll multiply by 1 minute equals 60 seconds. I'm multiplying by 1, just converting the units. Now the minutes cancel. I have per second like that. Right? And then I want feet per second, not inches